Today I'll be talking about why Jar Jar Binks is the most powerful Sith Lord in all of the Star Wars universe. I am kidding, of course. It is April Fool's, and I had to have some fun. Today I'll be talking about AI and machine learning workflows in Deephaven. This is going to be a relatively short presentation, um, and I hope to just touch on some key points in terms of problem solving with AI and machine learning, and some special considerations if you are using Deephaven and Deephaven Learn. So with that said, I'll get into a quick overview and touch on the four main steps of problem solving with AI and machine learning. These steps aren't all that different from a typical problem-solving workflow, with the four being to evaluate the problem, to set up a data source, and then define and construct a model, and lastly, to actually use your model in a training, testing, and evaluation phase. And so there's some questions you want to ask at each step. And the first and foremost is AI and machine learning the best solution? And the answer is not always yes. It's very problem specific. In particular, if you're solving anything in the field of pattern recognition, or you want a system to adapt to new and unexpected inputs, AI and machine learning does tend to work pretty well, but there are some real constraints there. Not only that, but what kind of AI and machine learning model will work best? I'll touch on this a little bit more later down the line. There are certain problems which different approaches are better designed to solve. For instance, classification problems, typically clustering and unsupervised learning methods tend to work really well, whereas sometimes there are some real constraints with using some things like artificial neural networks. And then, again, what will your constraints look like, as well as the inputs and outputs to your model? So in the case of Deephaven and using Deephaven Learn, the inputs specifically have to be strongly considered because of the way data is transferred between Deephaven tables and Python in the form of NumPy arrays. Next up is a data source. So in terms of Deephaven, you'll have probably a static table for training, or perhaps a pandas data frame or a NumPy array. Training is typically done in a static context, whereas your actual solution can be employed in real time with Deephaven. And so when it comes to a data source, it's a question of what do you want to use? Do you want to use a static Deephaven table? Do you want to use a pandas data frame? Do you want to use a TensorFlow tensor? And so on and so forth. And additionally, what is the minimum amount of data that you actually need for your model to achieve sufficient performance? So in terms of training a model, what is the minimum number of data points, of observations that you need to train your model on? How many epochs should you train your model for? And what is a batch size that you want to feed to your model? And there are drawbacks to there are ways in which you can choose all of these things. And sometimes, honestly, it's just fun to brute force, especially with training the number of epochs and your batch size. It's kind of fun to play around with and see how your model performs differently as you change those. Up next, you'll define and construct a model. So once you've picked out what approach you want to use, what is the best way to define the model? A lot of people like to talk about deep learning and these really deep neural networks that implement maybe convolutional layers and LSTM layers. But at the end of the day, if you can make a solution simple, that's probably the best way to do it. So depending heavily on the complexity of the problem you're trying to solve, you want to basically minimize the complexity of the model you're going to implement. And then last is to actually use your model. And so this will come in 3 separate phases, although there can be a fourth and possibly a fifth. And the first of those phases is to train your model. In the case of unsupervised learning, this step is called fitting. But basically, you have a set of training data. And in the case of supervised learning, that data has a set of labels which your model will attempt to correctly guess. And in the case of unsupervised learning, there are no labels, and so your model will just kind of give its best guess, but it doesn't really know what the answer actually is. And then in terms of things to keep in mind when it comes to particularly training, is how much time does it take to perform these steps. So for training, deep learning tends to take a very long time. So this is where you may want to leverage hardware that you have, whether it's a TPU or a CUDA-enabled graphics processor, things like that. As far as the testing phase, testing is where you have a second set of data that looks just like your training set, and you will test it on data that you that looks just like what you train your model on, and you see how it performs. And then to evaluate your model typically is where you'll deploy it in the real world, or you'll have a separate validation set that will hopefully look sufficiently different enough from your testing data to see how your model deals with unexpected data. In particular with Deephaven, one big question is, can your model keep up with real-time data? That's the best part about using Deephaven, is that the transition from static to real-time data is made easy. And so the biggest thing to consider is how much data will you be receiving in a given second and in a given update cycle, and depending on the length that it takes your model to actually process this data, can it keep up with how much you're receiving in either an update cycle or a second? And then lastly, if your model cannot keep up with real-time data, are there ways to improve speed and performance? Or perhaps if your model takes 5 days to train on a couple days worth of training data, are there ways you can improve it to not spend so long training? So I'll go into each step a little bit in more detail. And so the first step is to evaluate the problem. And this isn't specific just to AI and machine learning. This is something you should do anytime you're trying to solve any problem. But in particular for AI and machine learning, you want to determine if it's the best solution. For instance, one good example here is there are a wide number of models that are used to play chess and other games. But before AI and machine learning became popular, it wasn't really considered a solution for this problem. The best chess computers didn't use AI and machine learning. And then people quickly realized that if you train these AI and machine learning models, that they quickly surpass their non-AI counterparts. I believe the strongest chess computer nowadays plays itself something like 1 million times a day, every single day, to keep improving, which is kind of wild. But anyway, AI and machine learning tend to be the best solutions for a wide variety of categories of problems. In particular, the ones I have listed on the left. But it's not entirely the case. So there are a lot of specifics to get into in terms of whether or not you want to use AI and machine learning for your solutions. As far as what kind of inputs and outputs and constraints will look like, things to consider are the dimensionality and type of your input data. And this will vary from problem to problem. And not only that, but depending on what kind of AI model you're working with, the dimensionality of your input data may not match what the dimensionality of the data that your model expects. So for instance, in, I believe, PyTorch and TensorFlow, if you use an LSTM network, which is long short-term memory, both of those expect data in at least 3 dimensions, if not 4 dimensions. So you have to know not only what dimension your input data is, which is likely 2-dimensional when you're working with Deephaven Learn, but where you need to add those extra dimensions. Not only that, you need to know how much data your model is going to output in terms of an answer. Maybe it will output a discrete probability distribution, and maybe all you want is the element in the distribution with the highest probability, and that's its quote-unquote best guess. Or maybe you want that whole distribution and then to make decisions from there. You also, once again, have to consider how much time it's going to train the model. Again, if it's going to take a full day to train a model, you need to make sure that you leave yourself enough time to train it before you want to deploy it. And then lastly, once again, the time it takes to train model to be applied to real data, which hopefully is significantly less than the amount of time it takes to actually train the model. So for Deephaven in specifically, When it comes to evaluating the problem, you have to consider how the raw data is going to be processed into Deephaven. You also have to consider how, once you have a data source in the form of a Deephaven table, how that's going to translate to NumPy, because Deephaven Learn transfers data to and from Deephaven tables and NumPy arrays. So if you need to work with something else in particular, say you're working with PyTorch, which requires that your data comes in the form of a PyTorch tensor, you first have to convert to NumPy, and then you can convert to PyTorch from there. And then once you're done performing your calculations, you'll go back to a NumPy array. Actually, sorry, you don't have to go back to a NumPy array as long as you tell Deephaven that it will grab a certain data point at a certain set of indices. And then so going from Python back to Deephaven, that is the outputs of your model. You need to determine how many of those outputs are going to be and what kind of columns you want to store those data, those values in. And then once you have the solution in the form of a Deephaven table, do you want it to be broadcast anywhere else? So setting up a data source in Deephaven specifically, your data may come from a Kafka stream or Parquet files, or perhaps you want to create a simulated stream using Dynamic Table Writer. Perhaps you have a CSV file. Any of these things can be used in addition to a Python script that maybe does web scraping, or you're looking at Twitter data. But regardless of all of that, you need to consider how much data is ingested per second and per update cycle. So in the case of training, if you're doing that in a static context, that doesn't, how much per update cycle doesn't matter, but the biggest thing to consider is what your batch size is going to be. It is pretty well documented, the trade-offs in terms of batch size. A larger batch size will usually result in faster training, but is more likely to find a local minimum of instead of the actual global minimum of a function that you're trying to minimize. So there are trade-offs in terms of how long your model is going to take to train, and whether or not it's going to find the actual best solution versus its perceived best solution, which may work pretty well, but not quite as well as what exactly you're looking for. Again, and then in terms of your data source, how many rows of data on a table are you going to need, and what types of data are contained within those rows? So NumPy, we transferred data from Deephaven tables to NumPy arrays. NumPy enforces only one data type per NumPy array. So for instance, if you have, let's take a look at a toy problem here. So in Deephaven, let's say you have a data source with 5 columns. You have an integer column, 3 double columns, and a byte column. And let's say you need all 5 of these data types in a NumPy array. You're going to have to create 3 separate NumPy arrays. You'll need an array of integers, an array of doubles, and an array of bytes. And so from there, you may end up using some other, or your model gets applied to these values, and you end up with a single integer and a single double value. And then there's a one-to-one correspondence between the integer and the double values, which can be transferred back into a Deephaven table. So the diagram on the right at the top is your data source, and then the arrow pointing down is the transfer of Deephaven table data to NumPy. And then from the second to the third step is applying your model, which gives you outputs. And then the third to the fourth step is transferring those outputs back to a Deephaven table. And this is just a kind of a simple example, but this particular type of diagram holds true for other types of problems as well. Because once again, when you transfer data to and from Deephaven, or from Deephaven to Python, you will need a separate NumPy array for each individual unique data type contained within a table. So in terms of defining and constructing a model, there are primarily four types of AI and machine learning you can implement. You've got unsupervised learning, supervised learning, semi-supervised learning, and then deep learning. And the latter 3 of those can kind of be grouped into one category, whereas unsupervised learning is a little bit different. In terms of what Python modules you'll probably end up using, I highly recommend scikit-learn for unsupervised learning problems. I've used that probably more than any of the other ones. I really like it. It makes your life pretty easy when implementing these things, and it contains a whole boatload of unsupervised learning algorithms. It also does contain functionalities for implementing artificial neural networks. However, I have found that I like TensorFlow at PyTorch a little bit better for those. In terms of the types of problems you can solve, unsupervised learning is particularly good at clustering and anomaly detection, as well as dimensionality reduction. So if you have, say, 30 dimensions of data and you only want to work with 3 or 4, unsupervised learning does have quite a few methods for that, in particular PCA, which is principal component analysis, SVD, and there's one other one that I used in a grad school project that I cannot remember the name of, but it was pretty sweet. And then in terms of supervised learning, this is where we get into what everybody knows of the artificial neural network, but there are quite a few approaches you can take to supervised learning with models. Either gradient boosting, random forest. When it comes to deep learning is typically used for a model to outperform a shallow neural network, as they call it, or perhaps to improve over time. Whereas once a supervised simple neural network is trained, it pretty much just will never get any better from that point. And then semi-supervised learning is something that I have never actually really done, and I don't know a whole lot about it. I would have liked to spend some time to explain that a little better, but hopefully for another talk in the future. So yeah, I have just a couple examples of Python modules there on the right-hand side. This is in no way comprehensive. There are an absolute boatload of these modules available, and with Deephaven you can use any one you want. Just keep in mind that if your model requires you to work with its specific data type, for instance, PyTorch requires you to work with torch tensors, you will need to transfer data from a NumPy array to a torch tensor. So in terms, like I just said, of these for Deephaven, the biggest consideration is probably which Python module you want to use. These are a few really popular ones here on the right-hand side. I have used 4 of these. I particularly like scikit-learn, as I mentioned earlier, and I've used TensorFlow and PyTorch quite a bit. I've used XGBoost a little bit. That one was pretty lightning fast, which was pretty cool. And I have yet to really play around with NLTK very much. So in terms of Deephaven, just once again, consider what type of data your module will require you to work with, and as well as the problem itself. There is a wealth of information online for pros and cons for each of these Python modules. But the good thing with Deephaven is it will play with all of these, and so long as you transfer the data to and from Deephaven to Python in the manner prescribed by our docs, that it will work. So as far as train testing and evaluating your model, this is by far and away the largest part of the problem-solving step. I mean, this is most of the work. So first, consider what is the minimum performance required. For instance, maybe you're you're classifying the iris flowers. This particular data set has 150 observations. Maybe your model needs to get at least 145 of those right. It's good to have a minimum requirement specified so that when you're first writing and evaluating a model, that you know a minimum threshold that you need to meet. As far as unsupervised learning goes, like I mentioned earlier, it is particularly good at clustering and anomaly detection and dimensionality reduction. There are a bunch of algorithms available that do that. In particular, I think that k-nearest neighbors and dbScan are fantastic for doing clustering and classification. As far as anomaly detection, there are isolation forests and local outlier factor models that work quite well, and then latent variable and dimensionality reduction, once again, principal component analysis, and SVD is not support vector, it's something else, and I'm blanking on it right now. As far as supervised learning, once again, everyone knows the artificial neural network, but there's a whole bunch of other algorithms out there that it would take me far too long to go into. And then for deep learning, reinforcement learning and deep Q learning in particular are good at are used for algorithms that should get better over time by using an objective in order for an agent to interact with its environment and in order to maximize the reward from taking an action. And then there's LSTM, which is long short-term memory, which is used to predict values in the future. So LSTMs are particularly popular in AI and robo investing systems. They are used all the time in order to predict the value of stocks, in order to give the users an indication of whether or not they should buy, sell, or take other action. And then, once again, which Python module should you use? For unsupervised learning, I recommend scikit-learn. I really like it. And then we have docs on TensorFlow, PyTorch, and scikit-learn. But there are a wealth of other ones out there. And if you understand how to use Deephaven Learn for AI and machine learning, the problem flow or the flow of a solution won't change depending on the model you use. So I think I copied this slide, but there's not a whole lot to consider when it comes to Deephaven for this step that I haven't covered already. Really, it's just, consider what kind of model you want to implement, how long it's going to take, and then set up. I highly recommend for doing this problem solving to set up the data transfer first and to best understand what kind of data you're going to be working with for your model. So that, I think, is it for my presentation. Does anyone have any questions? I apologize. I would have liked to give some code examples here, but I didn't quite have as much time as I would have liked to prepare this week. So perhaps for a learning session in the future.
Can you talk a little bit about cases where inputs or outputs may not be NumPy?
You mean like for module specific, or?
Just in terms of the Deephaven Learn.
Yeah, so in particular, as PyTorch expects data in the form of torch tensors. So when you're using Deephaven Learn, which I think I have Deephaven over here. Hopefully that's not what I wanted. I want to share Deephaven. Anyway, so in terms of when you need to work with something that's not NumPy arrays, NumPy most Python modules allow you to transfer data to and from NumPy arrays, and that particular module. I know that Torch has a function called from NumPy that just does a one-to-one transfer of data. In addition, Pandas is very commonly used for AI and machine learning problems in traditional Python code. So Pandas is actually directly backed by NumPy arrays. So if you have a NumPy array, I don't remember what the exact function name is, but all you do is give it a set of column names and the NumPy array itself, and it will very quickly create the NumPy array. I'm not too familiar with other modules and if they require you to work with data not in the form of NumPy arrays. I know that XGBoost does have its own data structure, but I haven't really used it very much. So that transfer will happen inside of your gather function, which is what specifies how the data transfer occurs. So when you call Deephaven Learn, you'll specify a set of input columns. So maybe you have an X and a Y column. And once you specify those columns, you'll specify the gather function. And the gather function itself will return the output of a method called table to NumPy2D. And then, when you return that method, you can just wrap the method in whatever module you're using. So in the case of using Torch, your gather function will then instead return torch.fromNumPy. And then inside of that function call, you'll give it the table to NumPy2D method.
Great, thanks. Any other questions?